It's Alexi Demers again, an IoT software engineer working at Yocto. We're getting back to the embedded Linux subject today. We will address how to, in Yocto, handle multiple hardware variants of a product. This video is separated in two parts. The first part will address how to handle the hardware variants when the CPU is the same, and in the second part of the video we will address how to handle these variants when the CPU differs. So I'm going to start with a little plan of this video. We'll start by showing you some context, so what we're going to address today. Then we'll show you two approaches for managing hardware variants of a product. Then we'll dig into the usually preferred approach that our customers tend to go to when addressing hardware variants of a product. Now, here's the context. Let's say that on the left we have product 1 with hardware variant 1. And on the right, we have the same product, so still product 1, but a hardware variant 2. That's a common use case we have with a lot of our customers. So on the left you have one PCB, on the right you have almost the same PCB. You have a common CPU module, so the same little blue square there. But on the left variant of the product you have an audio codec, for example, and then a LoRa radio, for example. And on the right you would have probably an LCD display or an LTE radio, for example. So both are variants of the same product with little features that differs in the hardware, but all other features except the one I'm showing you there are the same, basically. So we'll address how can we develop a Yocto image for these products that is as efficient as it can be. There are a few approaches for addressing this kind of context, and we'll dig into the two most common one. First would be to generate different Linux images for every variant. So every Linux images has the correct configuration for the hardware variant it is running on. This approach has many cons and many pros, so let's look at some of them actually. First of the pros would be that it makes it easy to detect the type of product from the applications, since the image is able to have some little specificities that will allow user-space applications to detect what hardware it's running on from the image itself. Then it's a bit less error prone, because probably that your image that's running on variant 1 will not contain the stuff from variant 2, so it's not possible to mix up stuff between variants. Then Linux image is probably a bit more optimized for the same reason as I just said. And then development is a bit easier, since the image are the specificities of the image are generated at build time. Runtime detection of hardware functionalities is always a bit more complex. Then the cons of having different images for all variants is that for the production floor, that often makes it hard to handle the different variants, because they won't have exactly the same programming flow, and often on production floor that makes it more complex and more difficult to handle. And then the OTA updates mechanism will have to handle the different images because they are not compatible. Hardware variants have their own image, and you cannot mix up the images and the hardware variants, for example, so that can be a big blocker. And then second point, there will be multiple device software to support. You'll have to test all of the images more deeply, because dependencies could probably not be respected in one image or in the other, so that implies probably more QA tests. Let's now look at the approach number 2. In this case, we're going to use the same Linux image for all hardware variants. That's usually the preferred approach because of the pros and cons I'm going to show you right now. First pro is that, of course, the opposite of the previous approach. The production floor and the OTA updates mechanism will have to handle only one update file, so that makes it a lot more easier to handle. And of course, there is only one software to support. The cons are, of course, probably mostly the opposite of the approach number 1, is that it's a bit more error prone, because there's still a possibility that we load hardware specificities that doesn't apply to the current variant from the software side, because it's made at runtime. And selecting the correct features at the lower levels can be a bit more challenging. There is probably a little stuff that is implied in the bootloader to be able to tell the kernel what current hardware is there, and probably the application will have to detect what hardware it can access or cannot, for example. And then the Linux image size can be a bit bigger, but usually that shouldn't be that much, but it depends on the case, of course. Let's now have a look at what it should look like in your Yocto repository if you want to generate one single image that can manage different hardware variants of the same product. Here we are in the repository, which the URL is right here. This repository is meant to generate images for this kind of device I'm showing you right here. Orange Pi device, some generic device that looks like a Raspberry Pi actually. And we'll look at how this repository is handled to generate such an image. Here, let's look at the directory tree. Actually, we have a build folder, we have a layers folder, readme, documentation, and little script to start bit-baked stuff. So the build directory, as usual in Yocto, it's where the Yocto build output will be located, but also the configurations for the current build. We could use different build directories to generate different images, but since we're going to generate only one, we'll have only one build directory. So let's go into this one. And in the configuration folder, I believe you should be a bit aware of how Yocto works to know everything. So I invite you to go into the Yocto tutorials if you are not aware of what I'm talking right now. Configuration directory should contain, of course, the main element is the local.conf for the bblayers.conf, but we'll have only one local.conf file that should specify our machine and then our distribution mainly. Which should be the same for all image for the image we're using and should handle all of the hardware variants we have. So let's get back a bit. Right here. You should have in your layers directory this kind of structure. Let's take a look at it. We have different layers. Yes, the Poke layer, the meta virtualization, because in this case we have Docker installed. Then we have meta open embedded, meta arm, okay. Then we have the two custom layers here, which the first one is the BSP layer. So it's called Meta Orange Pi R1 Plus BSP in this case. And we have the Meta Blink OS, which is the distro layer. Usually we add -distro at the end. In this case, it's not there, but it's as you wish. Meta Orange Pi R1 Plus distro should contain all the stuff to handle all of your hardware variants. It should contain the kernel, it should contain the machine definition, which we can take a little look at right now. If I go into this one, and then I go into the conf and then machine folder, you can see that there is a little machine definition. In this case, we have two machines definition, but in your case, you should expect to have only one machine because you're generating only one image that supports all. And in this layer, the BSP layer can contain itself the device trees that should indicate to your application which hardware is currently enabled. So we'll dig into how to add the different device trees into Yocto, package them in the image, and use them so that your hardware features are enabled correctly and that your end user application can detect what's enabled and what it can use actually. And then when I'm talking about the distro layer, this should contain stuff that's normally unaware of the hardware it's running onto. A lot of customers will simply omit that layer. You could put everything into the BSP layer in our current case, because we're not probably going to run this software on another hardware with different CPUs or something like that. So you could put everything there, but I strongly suggest to still use a distro layer in your application, simply because it helps the decoupling of the functionalities, it helps logical separation of concerns, and in the future, if you ever have to put some little features that are not hardware aware onto another product, for example, it would be a lot easier to reuse. Even though probably that if you only have one product for now, the BSP layer and the distro layer may be coupled at some time, but keeping the separation there anyways helps for future improvements. In the rest of the video, we will look at how we can modify the BSP layer of the preceding Yocto repository to enable runtime detection of the hardware features. This can mostly be done from the bootloader actually. If you use U-boot, for example, it could read a GPIO encoded product ID and then select either different device trees, depending on the hardware variant it's running on, or different device tree overlays. Then user space applications will be able to read easily the hardware product, the product variant you're running on, and then select what features it can enable depending on what's the hardware it's running on. So, more precisely, in our case, we're going to use different device trees. Device trees can be organized in hierarchical way so that you don't duplicate code between the variants, and you only add little parts of device trees depending on the hardware variant you're running on. There is another option that could use a common device tree for both variants and different device tree overlays to enable specific features on either one variant or the other. This is interesting. But when we're talking about different variants that are almost the same, the hardware is not that much different. It's not that much useful because it has other drawbacks, like there is less verification of the device tree overlays validity at build time, for example. We're going to use most the overlays when we talk about different variants that have different CPUs or variants that can have optional modules that can be plugged on them, or different mezzanine boards, for example, so that you can mix different base device trees and different overlays to enable the different options you have on your product. But we'll dig into the case where we have completely different device trees. I say completely different, but as I said, device tree enable the reuse of common parts between the different variants. So it's time to explore how we're going to do that into Yocto. So we'll see how to define multiple device trees in Yocto and how to select one at runtime with little hands-on example, and how to extract the product type from the device that was selected actually. So now I have opened the BSP layer I was showing you before, so Meta Orange Pi R1 Plus BSP, in which we have different folders. You should probably be familiar with them. We'll go into the recipes kernel and then into the Linux folder. In this one we have two different files, so the definition of the Linux kernel, and then we have a definition of the different device trees. So this is the recipe that will handle the device trees. I'll go straight to the files folder here, in which we have the two different device trees that are supposed to handle either variant 1 or variant 2 of the product. If I open the first one, you can see that it's a kind of a small device tree with defining mostly differences into the GMAC to I/O, so in the Ethernet connectivity of this device. You can note that I can include from this device tree another device tree that you cannot find on the left here. This device tree is in the main kernel tree. So you'll see how Yocto can handle including other files that are in the kernel tree, even if they are not defined right here. So you can include any other device tree and appends and stuff over it. And that makes a little link with the device tree overlay I was showing you before. You can easily add little tweaks to device trees that are in the main Linux kernel without having to create device tree overlays that should be managed at runtime. So now we're all doing the modifications to this device tree here from another device tree that is over it, and that will be generated at compile time. Then you have the variant 2. The difference between the two device tree here is only the model name here, which is Practical IoT variant 2 in this case and Practical variant 1 in the other case. Let's see how we can integrate that into our Yocto image. If I take a look at the Linux Orange Pi device trees recipe here, you can see this is a little functional recipe that's supposed to install DTB files onto my final device. Into the target. Summary, license, of course, we have a little comment saying that all the files which are contained into the src URI here, if they end up with the DTS extension, will be compiled as DTB files and installed into the /boot/device tree folder on the target device. This is all made thanks to the device tree.bb class, which is inherited there. You can take a look at it if you want, but this will do all of the process needed to compile and to install them directly into that folder actually. Here I just wanted to show you how you can integrate into a bootloader, so in this case U-boot, a script file that would allow you to select either one DTB or the other. As I just said before, they are installed on your target right now. If you use the same little recipe as I've shown you before, it's installed in /boot/device tree, so U-boot should be able to select one or the other before starting the kernel actually. So if you look at uboot.inc file I'm showing you here, which is in the Pokey repository, you can find that the uboot_env variable can help you select the U-boot environment that should be packaged into your bootloader, which should allow you to do some scripting using U-boot to select the correct device tree. But in the example, I'm going to modify the U-boot environment directly on the running device to select one device tree and the other, and show you how I can detect which hardware I'm running on. So now let's look at how I can select one device tree or the other based on the hardware variants I'm running on. Note that what I'm going to script here can be saved as a U-boot environment file into Yocto directly, as I just mentioned before. Here, in the case of my device, I have a variable which is called DTB, like this, which currently contains the hardware variant 1. In U-boot, you can decide to read a GPIO to detect which hardware variant you're running on, and then you could decide to change your DTB variable to anything you want. So in this case, I'll try to change it to variant2.dtb, for example. In your case, the variables could be anything else. You have the complete control over the scripts in U-boot. So let's boot the device right now with this new device tree. So now that I'm logged in my device, I can find which device tree was selected, so which hardware variant I'm running on, by simply finding an information from the device tree, which is located into the folder I'm going to show you right now. Remember in the previous parts of this video that the modal property of the device trees was different depending on which device tree we were looking at. So here I should be able to find the string I was telling you before. Practical IoT variant 2. Sorry for the carriage return that doesn't exist at the end. That's how device tree manage the property, so there's no choice in this. But let's see, you see that now I can find from the user space applications which variant I'm running on. So this marks the end of this video. I hope you enjoyed it. It will help you handle the different hardware variants of your products. If you like these videos, don't hesitate to subscribe.